Swayam Prabha. Digital India. Educated India.
Now, let us go to discuss the projection perspective. In the following, we will derive a PCA as an algorithm that directly minimize the average reconstruction error. So, this perspective allows us to interpret PCA as implementing an optimal linear autoencoder, and we heavily draw the pictures. In the previous section, we derived a PCA by maximizing the variance in the projected space to retain as much information as possible. In the following, we will look at the difference vectors between the original data xn and their reconstruction xn bar and minimize the distance so that xn and xn bar are close as possible. Figure 10.6 illustrates this setting. So, figure 10.7 is a dimensional reduction with PCA, principal component analysis, and A is a setting of the vector projected on one dimensional subspace in R square spanned by B, and then figure B represent the x minus x bar. I bar is a mean difference. For the difference xi bar are shown in the red line. So, this is the picture representation of simplified the projection setting, and we have a setting and objective of the problem. Assume an ordered orthonormal basis O and B, where B equal to B1 to Bd of R power D, where Bi transpose Bj equal to 1, if and only if I equal to j and 0 otherwise. So, we know that for the basis B1 Bt of R power D, so x in R power D can return as a linear combination of the basis vector of R power D, that is x equal to summation d equal to 1 to d tilde d into b suffix d, which is equal to summation m equal to 1 to m tilde m bm plus summation j equal to m plus 1 to d tilde j bj. For suitable coordinate tilde d belongs to R. So, we are interested in finding the vector x in R power d, which live in lower dimensional subspace u in R power d. So, that dimension of u equal to m. So, that x tilde equal to summation I equal to m equal to 1 to m zm bm belongs to u in R power d is similar to x possible. Note that this point we need to assume that the coordinate zm of x tilde and tilde m of x are not identical. So, this is the construction of the setting and objective of the function of orthonormal basis, and the following we use exactly this kind of representation of x bar to find the optimal coordinates z and basis vector b1 to bm such that x bar is similar to the original data point x as possible. So, that is, we aim to minimize the Euclidean distance norm of x minus x bar. So, the previous figure illustrates the setting. So, without loss of generality, we assume the set of n vectors, that is xn belongs to R power d, is centered at the origin and expectation of x is 0. So, without the 0 mean assumption, we would arrive at exactly the same solution, but the notation would be substantially more cluttered. So, we are interested in finding the best linear projection of x onto a lower dimensional subspace U of r power d with the dimension of U equal to m, and orthonormal basis B1 to Bm. So, we will call this subspace U is the principal subspace. Therefore, the projection of data points are denoted by xn tilde equal to summation z suffix mn into Bm. So, which is equal to B into Zn belongs to r power d, where Zn equal to Z1n comma Zmn transpose belongs to r power m is a coordinate vector of xn bar with respect to the basis B1 to Bm. More specifically, we are interested in having xn bar as similar as xn as possible. So, the similarity measure we use in the following squared distance Euclidean norm, norm of x minus x bar square between x and x bar. So, we therefore define our objective minimization average squared Euclidean distance, that is a reconstruction error Jm equal to 1 by n into summation n equal to 1 to n norm of xn minus xn bar square. So, we make it explicit that dimension of the subspace onto which we project the data is m. In order to find this optimal linear projection, we need to find the orthonormal basis of the principal subspace, and the coordinate Zn belongs to r power n of the projection with respect to this basis. So, to find the coordinate Zn and the ONB of the principal subspace, we follow two-step approach. First, optimize the coordinate Zn for given ONB of P1 to Bm. Second, we find the optimal ONB. Okay, orthonormal basis of principal component analysis. And next, finding the optimal coordinate. Let us start to find the optimal coordinate Z1n and so on Zmn of the projection xn bar for n equal to 1 to n. So, consider figure 10.7b where the principal subspace is spanned by a single vector p. Geometrically we speaking, finding the optimal coordinates z correspond to finding the representation of linear projection x bar with respect to b that minimizes the distance between x bar minus x. So, from the figure 10.7b it is clear that this will be orthogonal projection. Therefore, we will show exactly this. Assume ONB of B1, B2, Bm of u belongs to r power d, and to find the optimal coordinates Zm with respect to the basis. So, we require the partial derivative dou Jm by dou Zin equal to dou Jm by dou xn bar into dou xn bar by dou Zin. So, dou Jm by dou xn bar is nothing but minus 2 by n xn minus xn bar whole transpose belongs to r power 1 cross d. So, let it be 30n 30b. Therefore, the dimensional reduction with the principal component analysis says that the picture A deals about the distance of x minus x bar from x bar equal to Zn b, which belongs to span of b. So, this is the optimal projection of the vector x in R square onto the one dimensional subspace, and picture B is represent the x bar that minimize the distance in a panel, which is orthogonal projection onto u from A. So, the coordinate of the projection x bar with respect to the basis vector B, the blue line that spans u is the vector we need to scale B in order to reach x bar, that is from what yellow line to make the orange, and that will project and it forms the orthogonal projection with respect to the basis vector B and span u. So, this is the orthogonal projection and it reaches the optimal coordinate. Therefore, dou xn bar by dou zin according to 28. So, partially with respect to zin of summation m equal to 1 to m zm bm, and m varies from 1 to m. So, we have a bi where I varies from 1 to m such that we obtain dou jm by dou zin equal to minus 2 by n into xn minus xn bar whole transpose bi, which is equal to minus 2 by n of a xn minus summation m equal to 1 to m zm and bm whole transpose into bi. So, orthonormal basis equal to minus 2 by n into xn transpose bi minus zin bi transpose into bi, which is equal to minus 2 by n xn transpose bi minus zin. So, since bi transpose and bi are 1, and setting the partial derivative yields the immediate optimal coordinates zin equal to xn transpose bi equal to bi transpose xn. Here I varies from 1 to m and n equal to 1 to n. This means that optimal coordinate zin of the projection xn bar and the coordinates of the orthogonal projection of the original data point xn onto the one dimensional subspace that is spanned by bi, and consequently number 1, the optimal linear projection xn bar of xn is orthogonal projection, and the coordinates of xn bar with respect to the basis b1 to bm are the coordinates of the orthogonal projection of xn onto the principal subspace, and orthogonal projection is the best linear mapping given the objective, and the coordinates tilde m of x in 26 and the coordinate zm of x bar in 27 must be identical for m equal to 1 to m. Since u perpendicular equal to span of bm m plus 1 to bd is orthogonal complement of u which span b1 to bm. Now, we have a note: orthogonal projection with orthonormal basis vectors. Let us briefly recap orthogonal projection from the section. If b1 to bd is an orthonormal basis in r power d, then x bar equal to bj into bj transpose into bj whole inverse into bj transpose x, which is equal to bbj transpose x belongs to r power d, is orthogonal projection of x onto the subspace spanned by jth basis vector, and zj equal to bj transpose x is the coordinate of the projection with respect to the basis vector bj that spans the subspace, since zj bj equal to x bar. Therefore, figure 10.8b illustrate this setting. More generally, if we aim to project onto the m dimensional subspace r power d, we obtained orthogonal projection of x onto the m dimensional subspace with the orthogonal basis vector b1 to bm as x bar equal to b into b transpose b whole inverse into b transpose x equal to b transpose x. So, we define b equal to b1 to bm, which is equal to r power d cross m. So, the coordinate of this projection with respect to the ordered basis b1 to bm are z equal to b transpose x. So, we can think of the coordinate as a representation of projected vector in a new coordinate system defined by b1, b2 and so on bm. Note that although x belongs to r power d, we only need m coordinates z1 to zm to represent this vector. So, the other d minus m coordinates with respect to the basis vectors are b m plus 1 to bd are always 0. Next, finding the basis of the principal subspace. So, determine the basis vector b1 to bm of the principal subspace. We rephrase the loss function 29 using the results we have so far. This will make it easier to find the basis vectors. To reformulate the loss function, we exploit our result from before and obtain xn bar equal to summation m equal to 1 to m zm and bm. As per the 32, we can write zmn as xn transpose bm, and so the equation reduces to summation m equal to 1 to m xn transpose bm into bm. So, we now exploit the symmetry of the dot product, which yields xn bar equal to summation m equal to 1 to m bm into bm transpose xn. So, we have the picture of the dimensionality reduction with the principal component analysis. So, this shows that the orthogonal projection and a displacement vector, when the projection data points is xn is a blue onto subspace un, we obtain xn bar is a orange. So, displacement vector xn bar minus xn lies completely in the orthogonal complement u2 of u1. So, since we can generally write the original data point xn as a linear combination of all basis vectors, it holds that xn equal to summation d equal to 1 to d z suffix dn bd. According to 10.32, we can write zdn is xn transpose bd into bd, where d varies from 1 to d. So, that after simplification bd transpose the xn will come. Now, we start with d equal to 1 to d. So, that m stands for 1 to m and m plus 1 to d. So, first part replace d to m and bm transpose into xn will come. Second part m plus 1 to d bj into bj transpose xn. Now, we split the sum with the d terms into sum over m and sum over d minus m terms. With this result, we find the displacement vector xn minus xn bar. So, the difference vector between the original data point and its projection is xn minus xn bar equal to summation j equal to m plus 1 to d bj transpose into xn. So, which is equal to summation j equal to m plus 1 to d xn transpose into bj Now, as per 3.8, this means the difference is exactly projection of the data point onto the orthogonal complement of the principal subspace. So, we identify the matrix summation j equal to m plus 1 to d of bj transpose as the projection matrix that performs this projection. Hence, the displacement xn minus xn bar lies in the subspace that is orthogonal to the principal subspace as illustrated in the figure 10.9, and we have what orthogonal to the principal subspace. So, we have a note to low rank approximation. In 38A, we saw that the projection matrix which project x onto x bar is given by m equal to 1 to m bm transpose, which is equal to bb transpose. So, by construction as sum of the rank 1 matrices bm transpose, we see that bb transpose is symmetric and has rank m. Therefore, the average squared reconstruction error can also be written as 1 by n to summation n equal to 1 to n norm of xn minus xn bar square, which is equal to 1 by n into summation n equal to 1 to n norm of xn minus bb transpose xn square. So, this becomes 1 by n into norm of xn to 1 is I and bb transpose to xn square. So, for finding orthonormal basis vector b1 to bm, which minimize the difference between the original data xn and the projection is xn bar is equivalent to the best rank m approximation bb transpose of the identity matrix I. So, we have all the tools to reformulate the loss function. Therefore, Jm equal to 1 by n summation n equal to 1 to n xn minus xn bar square. So, according to 38b, it becomes 1 by n into summation n equal to 1 to n. J varies from m plus 1 to d bj transpose xn into bj square. So, we now explicitly compute the squared norm and exploit the fact that the Bj form an ONB. So, this yield Jm equal to 1 by n summation n equal to 1 to n and j equal to m plus 1 to d Bj transpose x1 square. Therefore, 1 by n equal to summation n equal to 1 to n j equal to m plus 1 to d Bj transpose xn Bj transpose xn. So, 1 by n into summation n equal to 1 to n j varies from m plus 1 to d Bj transpose into xn xn transpose Bj. So, we exploit the symmetry of the dot product in the last step to Bj transpose xn equal to xn transpose Bj. Now, we swap the sums and obtain Jm equal to summation j equal to m plus 1 to d Bj transpose into 1 by n to summation n equal to 1 to n xn xn transpose Bj. We call this as S, and this equivalent to j equal to m plus 1 to d Bj transpose into Sbj. Now, we have to find the trace of Bj transpose Sbj, where j varies from m plus 1 to d. So, summation j equal to m plus 1 to trace of Sbj Bj transpose equal to trace of j equal to m plus 1 to d Bj Bj transpose S. This is called as projection matrix, and we exploit the property that a trace of an operator is a linear and invariant to cyclic permutation of its argument. Since we assumed that our data set is centered, therefore, expectation of x equal to 0, we identify that S as the data covariance matrix. Since the projection matrix is constructed as a sum of rank 1 matrices Bj Bj transpose itself a rank d minus m. So, the equation 43 implies that we can formulate the average square reconstruction error and equivalently as the covariance matrix of the data projected to orthogonal complement of the principal subspace, and minimizing average square reconstruction error is therefore equivalent to minimize the variance of the data when projected onto subspace we ignore, that is the orthogonal complement of the principal subspace. Equivalently, we maximize the variance of the projection that we retain in the principal subspace, which links the projection loss immediately to the maximum variance formulation of PCA, principal component analysis, discussed in this section, but this is also mean that we will obtain the same solution that we obtained the maximum variance perspective. Therefore, we omit a derivation that is identical to the one presented in this section and summarize the result from earlier in the light of the projection perspective. Now, this is the picture shows that the embedding of M1IST digits of 0 and 1, and 0 represent the blue and 1 represent the orange in a two-dimensional principal subspace using the principal component analysis, and the 4 embedding of digits 0 and 1 in the principal subspace are highlighted in red with their corresponding original digit. So, this visualize the training data of M1IST digits 0 and 1 of the embedded in the vector space spanned by the two principal components, and we observe that a relatively clear separation between zeros and 1, and we can see the variation within the each individual of the cluster. 4 embedding of the digits 0 and 1 in the principal subspace and highlighted in red and their corresponding original digit. So, the figure reveals that the variation within the set of 0 is significantly greater than the variation within the set of 1. Further, we note the training and testing errors let us take the closer look at the architectural machine learning task of classifying handwritten digits. We use the simple digit benchmark data that you know from the section. So, the task is specified as follows. One is a training data. So, xi train and ci train, I varies from 1 to 1000 data, where xi train belongs to 0, 1 of 240. 240 represents 240 dimensional image vectors whose component is corresponding to 15 into 16 pixels, which have normalized grayscale values ranging from 0 to 1, and where the ci train are class labels from the set 0 to 9. So, there are 100 examples from each class in the training data set. So, test data, another set is xi test to ci test, where I varies from 1 to 1000, also having 100 examples of each digit. Next one is a task specification. So, this is a benchmark data set with a standardized task specification. Train a classifier using the training data, then test it on the test data and report the rate of misclassification. So, the loss function is thus count the loss given in the expression. So, an elementary yet professionally structured learning pipeline which use methods that we have already described in the course goes as follows. So, it may be welcome rehearsal to give step by step instruction. First stage, dimension reduction by principal component analysis. Number 1, center the data of data set of the image vectors by subtract the mean vector mu, obtaining the x training. Number 2, assemble the centered image vectors column wise in 240 into 1000 matrices X. Compute the correlation matrix C equal to 1 by 1000 into X into X dash, and factorize C into a singular value decomposition, where C equal to U summation U dash. The columns U are the 240 principal component vectors of C. Decide how strongly you want to reduce the dimension, shrinking it from n equal to 240 to m less than n. Let um be the matrix from the first m columns from U, and project the centered patterns xi train on the m first principal components obtained by m dimensional future vectors, that is f power train equal to um dash of x bar train. Now, we have to vectorize the class labels by one hot encoding. So, each ci train is rewritten as a binary 10 dimensional vector of a vi train, which has one entry in the corresponding class ci. Assemble these vector column wise in 10 into 1000 matrix V, and compute linear regression classifier. Assemble the 1000 m dimensional future vectors f suffix I train into m cross 1000 dimensional matrix F, and we obtain 10 cross m dimensional regression. So, we have a weight matrix W dash equal to f dash whole inverse into f into V dash, and compute the training MSC and training the error rate. So, the training mean square error is given by MSC train equal to 1 by 1000 into summation I varies from 1 to 1000 of norm of Vi train minus W of Fi train square, and compute the train MSC and training error rate. The training mean square is given by MSC train equal to 1 by 1000 into summation I equal to 1 to 1000 of norm of Vi train minus W Fi train square. So, the training misclassification rate is Q train equal to 1 by 1000, where I varies I such that maximum of ind W Fi train minus 1 is not equal to Ci train, where maximum ind picks the index of the maximal element in a vector. Note -1 is owed to the fact that the vector indices ranges from 1 to 10, while the class labels go to 0 to 9. So, similarly compute the test MSC and error rate by MSC test equal to 1 by 1000 into summation I equal to 1 to 1000 of norm of VI test minus W of FI test square, where Q test equal to 1 by 1000 into set bracket I such that maximum of in W FI test minus 1, which is not equal to CI test, where FI test equal to UM dash of X test minus mu. And note that for centering the test data, use the mean mu obtained from the training data. So, this is the procedure made from basic linear operation that you should master even when sleepwalking. With some practice, the entire thing should not take you more than 30 minutes for the programming and running. Although a handy, quick and not very dirty routine that you should consider carrying out in every classification task. So, in order to get a baseline before you start exploring more sophisticated methods. And now, let us draw that what is probably the most helpful graphs in these lecture notes, worth to the burnt into your subconscious, and figure 29 shows these diagnostics for all possible choices of the number M2 equal to 1 to 240 of PC feature used. So, the figure 29 dashed the train blue and test red MSC obtained from M equal to 1 to 240 PCs, solid train blue and test red miscellaneous rates. The y-axis the logarithm base of base 10. So, this plot visualizes one of the most important issues in machine learning and deserves a number of comments. As M increases, the x-axis the plot the number of parameter in the corresponding linear regression weight matrices W grows by 10 into M. More model parameter means more degree of freedom, more flexible models with greater M models can increasingly better solve the linear regression learning equation 20. So, this is evident from the monotonous decreasing of the train of MSE curve. So, the training miscellaneous rates also decreases persistently except the jitter that is due to the fact that we optimize the model only indirectly for low misclassification. So, the analog performance curve for the testing MSE and misclassification first exhibit a decrease followed by an increased tail. So, the testing misclassification rate is minimal for M equal to 34. So, the first decrease then increase behavior of the testing of MSE or classification rate is always observed in supervised learning task when models are compared which have growing degrees of data fitting flexibility. So, in our digit example, this increase in flexibility was afforded by growing numbers of PC features, which is turn gave the final linear regression a richer reporter of future values to combine into the hypothesis vectors. So, the increasing tail of testing MSE or classification rate is a hallmark of overfitting. When the learning algorithm admits too much flexibility, the resulting model can fit itself not only to what is lawful in the training data, but also to random fluctuation in the training data. And intuitively and geometrically speaking, a learning algorithm that can shape many degrees of freedom in its learned models allows the model to fold in curls and wiggles to accommodate the random whims of the training data, but then the random curls and wiggles of the learned model will be at odds with the fresh testing data. Now, we have an example of polynomial curve fitting. So, this example is the standard textbook example for demonstrating outfitting. Let us consider one dimensional input, one dimensional output regression task of kind, where the training data are of the form xi, yi in R cross R. Assume that there is some systematic relationship y equal to h of x. So, that we want to recover from the training data. So, we consider a simple artificial case when the xi range in 0 to 1 and the and the to be discovered true function relation y equal to sine of 2 pi x. So, the training data however contain a noise component, that is y equal to sine of 2 pi xi plus vi, where vi is a draw from normal distribution with 0 mean and standard deviation sigma. Figure 30 shows that a training sample of xi comma yi where I varies from 1 to 11. Here capital N is 11 training point xi are chosen equidistantly. So, we now want to solve the task of the learning a good approximation for h from the training data xi yi by applying polynomial curve fitting. An elementary technique you must be surprised to meet here as a case of machine learning. So, this is the picture considering an mth polynomial of p of x equal to w naught plus w1x and so on wm x power n. So, example of training data is a red square obtained from the noise observation of an underlying correct function of sine of 2 pi x dashed blue line. So, we want to approximate the function given to us through the training sample by the polynomial, that is we want to learn a polynomial p of x such that p of xi equal to yi. More precisely, we want to minimize the mean square error on the training data. Mean square error is 1 by n to summation I equal to 1 to n p of xi minus yi square. So, we do not bother how this task is solved computationally. So, we simply rely on MATLAB function polyfit which does exactly the job for us. So, given data point, the polynomial order m, find the coefficient wj which minimize the mean square error. So, the picture 31 is fitting polynomials of the green lines for the polynomial order 1, 3, 10 from left to right. So, this shows that the polynomial found in this way of m. So, if you compute mean square errors for 3 orders, we get mean square error training is 0.48, 0.07 and 0 respectively. So, some observation they are number 1, if we increase the order m, we get increasing the lower MSE train. For m equal to 1, we get a linear polynomial which apparently does not represent the original since the function is underfitting. M equal to 3, we get the polynomial that hits our target sign apparently quite well. M equal to 10, we get a polynomial that perfectly matches the training data but apparently misses the target sign function overfitting. So, the modeling is a flexibility is here defined through the polynomial of order m. If it is too small, the models are too inflexible and underfit. If it is too large, we see outfitting. However, please switch now into your most critical thinking mode and reconsider what I have just said. Why? Indeed, should we judge the linear fit underfitting? The order 3 fit seems okay. The order 10 fit overfitting. There is no other ground for justifying these judgments than our visual intuition and our secret mastermind knowledge. That is, the underlying pure function was this sine wave. In fact, the order 10 fit might be the right one if the data contain no noise. The order 1 fit might be the best one if the data contain a lot of noise. If we did not know beforehand that the true noiseless function was the sine wave, then we could not know which of the 3 cases from figure 31 give us the best model. Now, we have to go to the example 2 of a PDF estimation. Now, we are going to discuss the example 2 PDF estimation. Let us consider the task of estimating a 2-dimensional PDF probability density function over the unit square for 6 given training data points xi, I equal to 1 to 6, where xi belongs to 0, 1 to 0, 1, 0, 1 cross to 0, 1 cross. So, this is an elementary unsupervised learning task. the likes of which frequently occur as a subtask is more involved learning task, but which is of the interest in its own right too. Figure 32 shows 3 PDFs which were obtained from the 3 different learning runs with the models of increasing flexibility. So, I do not explain the modeling methods here for the one who know about it. So, the simple Gaussian portion window models where the degree of admitted flexibility was turned by kernel width will be explained. Again we encountered the fingerprints of under or overfitting. So, the low flexibility of model seems too unbending to resolve any structure in the training point cloud. So, the high flexibility model is so volatile that it can accommodate each individual training point, but again we do not really know. So, we are going to discuss the example 3, the learning addition boundary. So, figure 33 shows a schematic of the classification learning task where the training patterns or the points in R square are come into 2 classes. When the training model is too flexible, the addition boundary is confined to be a straight line. So, this figure estimates the probability density function from 6 data points. It is a model flexibility grows from left to right, and also we have to note the different scaling of the z axis. So, the integral of a PDF is 1 in each of the 3 cases. So, here we mentioned the top of this one is a 1. Now, presumably underfitting when the flexibility is too large. So, the each individual training point can be lassoed by sliding of the addition boundary, and presumably overfitting. And do I need the repeat that while these graphics seem to be indicate under or overfitting? So, we do not actually know. So, in figure 33 is a learning addition boundary for 2 class classification task of 2 dimensional patterns marked by X and O. Another example, the furniture design. The overfitting can also hit in your sleep, see the figure 34. Again, while this looks like a drastic overfitting, it would be just right if all humans sleep in the same folded way as the person whose sleep shape was used for the training the master's model. So, the interim summary is the 4 examples stem from different learning tasks: function approximation and PDF learning, classification learning, furniture optimization, and correspondingly the picture shows that the nightmare case of overfitting, pictures spotted by Yashin Sipok, and refer the website, no longer accessible, design and crafted by artist Dominic Wilkos in the year of 1999. Code first the artist description of the objects, and I used my own body as a template for the mattress from ML point of view. This means the size n equal to 1 is a training data set. So, the overfitting problem manifests itself in a different geometrical ways, but the flavor is the same in all classes. So, the model flexibility determines how wiggly the geometry of the learned model can become. So, very large flexibility ultimately admits to fold the model snugly around each individual training point. So, this leads to small even 0 training error, but it is likely disastrous for generalization to now test data point. Very low flexibility can hardly adapt to the structure of the training data at all. Likewise, the leading to poor test performance. Some interpret the flexibility will strike the best balance, and probably speaking, flexibility is not a characteristic of the final model that one obtained after learning, but of the learning algorithm. If one uses the term precisely, one should speak, for example, of the flexibility of the procedure to train a third order polynomial function, or of the flexibility of PCA based linear regression learning scheme which uses PCA features. Now, I introduced this way of speaking about the flexibility ad hoc. In statistics and machine learning textbook, you will hardly find this term. Instead, specific method to measure and time the flexibility of the learning algorithm have the specific names, and it is these names that you will find in the literature. The most famous among them is a model capacity. So, this concept has been developed in a field now called statistical learning theory. And not only, I consider it a highlight of the modern ML theory. So, we will however not treat the concept of the model capacity in this course, since it is not an easy concept and it needs to be spelled out in the different version of the different types of the learning task and algorithm. And check out the website if you want to get an impression, and also see the section will present two simpler methods for handling modeling flexibility, which they lack the analytical beauty and depth of the model capacity concept or immensely useful in practice. So, I emphasize that finding the right flexibility of the learning algorithm is an absolutely crucial for good performance of ML algorithm. Our little visual examples do not do justice to the dismal effects of the overfitting may have in a real life learning task, where a high dimension of the pattern is combined with a small number of training example, which is a situation faced very often by ML engineering in practical application.